Domain-adaptive lung nodule detection in X-ray images. Lung nodules are a crucial indicator of lung cancer, and early detection is vital for improving patient survival rates. Chest X-rays are widely used for lung nodule detection due to their cost-effectiveness and minimal radiation risk. However, the increasing workload poses challenges for physicians to effectively identify lesions in chest radiographs. To address this, researchers have developed automated lung nodule detection algorithms, but existing methods often struggle with domain shift issues when applied to data from different medical centers. To overcome these challenges, a novel domain-adaptive approach for lung nodule detection is proposed, leveraging mean-teacher self-training and contrastive learning. The approach introduces a hierarchical contrastive learning strategy to refine nodule representations and enhance the distinction between nodules and background. This strategy unfolds in two dimensions: region level and pixel level, capturing size and shape characteristics, as well as texture and grayscale features. Additionally, a nodule-level domain-invariant feature learning (NDL) module is proposed, featuring an adversarial gradient reversal layer and a domain classifier. This module aims to refine the model's performance by capturing finer details and addressing domain-adaptive challenges at the object level. The proposed approach tackles the challenge of low-quality pseudolabels by employing a distinct hierarchical contrastive learning strategy. Unlike previous methods, this strategy captures additional valuable information, such as the correlation between nodules and background, throughout the training process. To validate the effectiveness and generalization of the model, a new lung nodule detection dataset named B-nodule is constructed. The dataset is collected from collaborative hospitals and annotated by experienced radiologists. Experimental results demonstrate that the proposed approach effectively mitigates the domain shift issue and surpasses existing methods in performance. The contributions of this work include a novel lung nodule detection method based on the mean-teacher approach and contrastive learning, a hierarchical contrastive learning strategy, a nodule-level domain-invariant feature learning module, and a new annotated dataset of chest X-ray images for lung nodule detection. The proposed model integrates hierarchical contrastive learning into the mean-teacher model to enhance the accuracy of cross-domain lung nodule detection. This approach includes region-level and pixel-level contrastive learning, utilizing differences between foreground and background as supervisory signals for target data. The hierarchical contrastive loss is composed of both pixel-level and region-level losses, aiming to make nodules more alike in representation while making them more distinct from the background. In addition to hierarchical contrastive learning, the model also employs a nodule-level domain-invariant feature learning (NDL) module to align the two domains. This module focuses on aligning more detailed features, specifically the alignment of nodule-level features, rather than aligning source and target domains at the image level. After obtaining nodule-level features from the source and target domains, they are fed into a domain classifier. An adversarial gradient reversal layer (GRL) is introduced before the domain classifier to hinder the domain classifier from making accurate predictions, thereby addressing the domain-adaptive challenge in lung nodule detection. The teacher-student mutual learning process is initiated by training an adapted model using data from the source domain and obtaining the weight of the adapted model. The teacher model undergoes incremental updates using the student weights and follows an exponential moving average (EMA) approach, making it akin to multiple temporal ensemble student models. Experiments are conducted on 3 datasets, including Node 21, CXR2, and B-nodule. The B-nodule dataset comprises 1964 chest X-ray images and 2,314 annotated lung nodules, split into training and test sets to facilitate robust model evaluation. This paper presents a novel domain-adaptive method for lung nodule detection in X-ray images, focusing on the challenge of domain shift through the integration of contrastive learning and domain-invariant feature learning. The proposed approach is evaluated in cross-domain experiments on 3 datasets, demonstrating its effectiveness in mitigating the issue of low-quality pseudolabels and improving detection performance. The model's superior performance is attributed to the contrastive learning approach, which spans from region to pixel scales, enabling the acquisition of meaningful representations of both nodules and backgrounds. Furthermore, nodule-level domain-invariant feature learning aligns features between the source and target domains, thereby further mitigating the issue of low-quality pseudolabels. The paper also includes ablation studies on critical components of the model, such as contrastive learning and classifier loss, which show significant improvements in performance when these components are incorporated. The results indicate that the proposed method outperforms other established domain-adaptive object detection methods in both the CXR to B nodule and CXR to Node 21 scenarios. Here is the combined summary of pages 7 and 8. The authors provide an extensive review of existing works in domain-adaptive object detection, highlighting various approaches to tackle the challenge of adapting object detectors to new domains. They cite several studies that employ domain adversarial training, strong-weak distribution alignment, and prior-based domain adaptation to improve object detection performance in diverse settings, such as hazy and rainy conditions. The authors also discuss recent advancements in domain-adaptive object detection, including center-aware feature alignment, scale-aware domain-adaptive faster RCNN, and cycle-consistent domain-adaptive faster RCNN. Additionally, they mention works that focus on harmonizing transferability and discriminability for adapting object detectors. Furthermore, the authors highlight the importance of benchmarks for evaluating domain-adaptive object detection methods. They mention the CDTD benchmark, which provides a large-scale cross-domain dataset for instance-level image-to-image translation and domain-adaptive object detection. The authors also discuss the relevance of object detection in medical imaging, particularly in chest X-ray radiographs. They cite studies that employ deep convolutional neural networks for lung nodule detection and segmentation. In the context of domain adaptation, the authors discuss various techniques, including maximum classifier discrepancy, deep reconstruction classification networks, and contrastive learning. They also mention recent works on unsupervised domain adaptation, multi-resolution convolutional networks, and contrastive detection. The authors conclude by emphasizing the need for further research in domain-adaptive object detection, particularly in addressing the challenges of open-world object detection and unsupervised domain adaptation. They suggest that future studies should focus on developing more robust and efficient methods for adapting object detectors to new domains.